Hey there, you. Ever wondered what truly makes your smartphone or, your gaming console so incredibly fast and efficient? We often talk about the power of CPUs and GPUs, right? But beneath the surface, there's a whole fascinating, complex world of specialized silicon, stuff that has been quietly yet dramatically driving computing performance for decades. It's really the story of these unsung heroes, the architectural innovations that took our devices from just functional to absolutely mind blowing. Today, we're taking a deep dive into the architectural history of specialized computation. We're going to trace its evolution meticulously. We'll start from the humble beginnings, simple coprocessors, and go all the way to the incredibly powerful accelerators that define our modern digital world. We've got this fantastic report here, really comprehensive, just jam-packed with fascinating insights that illuminate this whole journey.
Yeah, and our mission today is really to unpack this profound evolution. We want to show how the concept of a coprocessor, and that term itself, has undergone a remarkable transformation, how it moved from being this optional, almost niche add-on to becoming essentially the fundamental building block of modern heterogeneous computing. We'll dig into the critical why behind these shifts, look at the challenges that demanded new solutions, and what all of this means for the incredible tech you use every single day.
Okay, get ready for some serious aha moments because by the end of this deep dive, I promise you'll never look at your devices the same way again. This isn't just a history of chips, right? It's like a testament to the relentless human quest for performance and how ingenious engineering repeatedly found ways to break through what seemed like insurmountable computational bottlenecks. Okay, let's unpack this first bit. We all kind of get the general purpose central processing unit, the CPU. It's the versatile workhorse of our systems, yeah. Designed for maximum flexibility, handles everything from the OS to file management, jumping between all sorts of different tasks. But when the workload shifts to highly specialized, computationally intensive stuff like complex floating point math or intricate signal processing or these massive parallel computations, well, the CPU's generalist nature starts to show its limits. It's built for breadth, maybe not always for extreme depth in one specific area.
That's precisely it. And the principle of computational offloading, basically, handing off specific hard jobs to something else. It's been a consistent theme since the dawn of microprocessors. The specific tasks needing offloading have changed dramatically over time, sure, but the underlying need for specialized hardware to handle them more efficiently, that's never gone away. I mean, if you look back at early 8-bit and 16-bit CPUs, for example, doing floating point arithmetic was incredibly slow, painfully slow. They had to perform these complex calculations using dozens, sometimes hundreds, of basic multi-instruction software routines. Imagine trying to do, I don't know, advanced calculus by hand, just using addition and subtraction over and over again. That's kind of how inefficient it was. This created a huge performance bottleneck, especially for emerging professional applications in science and engineering.
Right, so that bottleneck became a major roadblock, and that led directly to the development of the math coprocessor, didn't it? The FPU, the floating point unit. These were dedicated chips engineered just to do those floating point calculations directly in hardware, which was like way faster than the main CPU trying to fake it in software.
Orders of magnitude faster, exactly.
Hmm.
A landmark example, one that really brought this into the mainstream, was the Intel 8087. It came out as an optional companion to the Intel 8086 and 8088 CPUs, the ones in the original IBM PC. The 8087 was a total game changer. For users running scientific software, engineering programs, CAD stuff, it could speed up floating point math by a factor of 50, 50. But what's crucial to understand is, it wasn't a universal upgrade, it was optional. If you were mostly using your PC for, say, word processing, you could skip the extra cost.
Ah,
So it's
okay.
a really clear early example of how you could customize performance to your specific needs, balancing cost and capability.
That's pretty amazing, isn't it? To think you could literally choose how fast your computer did math just by slotting in an extra chip. But this tight integration and the fact it was optional, that must have created some headaches for software developers, right? I mean, what were the implications? Having to support systems with the FPU and systems without it?
That's a really perceptive question, and yeah, it highlights a crucial difference in design philosophy back then. The Intel 8087 was what we call tightly coupled. It basically watched the same instruction stream as the main CPU. When it saw instructions starting with an F, like F80D for floating point at it, it would just grab it and execute it. But if you didn't have the 8087 chip plugged in, the main CPU just didn't understand those F instructions. They were meaningless. So developers had two choices, neither great. Either make two completely separate versions of their software, one for FPU systems, one without.
Oh,
Or include really complex runtime checks to see if the FPU is there and dynamically adapt the code. This definitely complicated software distribution and, frankly, the user experience. Interestingly, Motorola, with their 68000 family and the 68881 and 68882 math coprocessors, they took a more elegant approach, a more seamless one. On a Motorola system, if the FPU wasn't present, the main CPU was designed to trap the floating point instruction. It would recognize it as invalid, trigger an exception, kind of like an error flag,
Right.
and then hand control over to a software routine that would emulate the instruction. Slower, of course, much slower than hardware, but meant a single program binary could run on systems whether they had the FPU or not.
Ah, that's much cleaner.
Yeah, it's significantly simplified software development and deployment. It really shows these different philosophies about hardware-software integration. But, ultimately, as silicon manufacturing got better and cheaper, transistor budgets grew. The cost of just putting the FPU logic directly onto the main CPU die dropped dramatically. So by the mid-1990s, those separate socketed math coprocessors, pretty much obsolete in desktops, the FPU just became a standard integrated part of the main CPU.
Okay, so while FPUs were speeding up personal computers, the supercomputing world was tackling an even bigger problem. How do you perform the same calculation but on massive data sets? We're talking things like computational fluid dynamics, weather forecasting, complex nuclear simulations, tasks needing extreme data parallelism, operating on millions of data points all at once.
Precisely. And the earliest attempts to tackle this huge scale, they go way back. Projects like the Westinghouse Solomon in the early 60s, and then culminating in the really ambitious Ilyasov computer in 1972. These were true array processors, designed from the ground up to implement what we call a single instruction, multiple data paradigm, or SIMD. Imagine a single conductor leading an orchestra. The conductor gives one instruction, say play C sharp, and every instrument plays that same note, but maybe at different volumes or timings. In Ilyasov, it was a single control unit broadcasting one instruction like add 5 to a huge array of simple arithmetic logic units, ALUs. Each ALU executed that identical instruction, but on its own different piece of data, all at the same time. Wow. The Ilyasov, it faced immense engineering challenges, fell short of some goals, but it conclusively proved the SIMD concept was sound. It worked. For certain data-heavy tasks, it was the fastest machine on the planet.
That's an incredible leap, just proving that concept of massively parallel execution. So taking that core idea, data parallelism, vector processing then emerged as another dominant approach in supercomputing, right? What was the idea there?
Yeah, vector processors evolved the idea. They used a highly pipelined ALU, think of pipelining like an assembly line in a factory. Instead of building one car start to finish before starting the next, different stages of building many cars happen simultaneously at different stations, increases throughput massively.
Right, right.
So these vector processors operated on one-dimensional arrays of data, called vectors. Early examples, like the CDC Star 100s from 74 and the Texas Instruments ASC from 72, used a memory-to-memory architecture. This meant vector data streamed directly from main memory through the computational pipeline, and the results streamed right back to memory. The big problem, the primary bottleneck, was the incredibly high latency of main memory back then. Getting data in and out was slow. These pipelines took a long time to fill up, so they were only really efficient with very, very long vectors. And they really struggled with scalar performance just doing single non-vector calculations. They weren't great at that compared to general-purpose machines.
Ah, the memory bottleneck, that old chestnut. A problem that's basically been around since computing began, and yeah, we still fight it today. But then came a massive breakthrough, didn't it? The Cray one, 1976. Seymour Cray. Our report says he had this critical insight that just revolutionized supercomputing.
He absolutely did. Seymour Cray's genius wasn't just about raw clock speed, though the Cray 1 was fast. It really underscored this foundational principle that's still true. Performance is ultimately dictated by how cleverly you manage and hide memory latency. He realized minimizing slow main memory access was everything. So instead of memory-to-memory, the Cray 1 introduced a register-to-register architecture. It featured 8 64-word vector registers. Think of these as an incredibly fast software-controlled cache physically right next to the processing units.
Okay, so keeping the data close.
Exactly. Data was first loaded into these fast registers. All the number crunching happened directly on the data within those registers, and only then were the final results stored back out to the slower main memory. This dramatically cut down on those slow memory accesses. And the Cray 1 pioneered other cool techniques too. It had multiple independent functional pipelines, so different kinds of math could happen at the same time. Even more impressively, it introduced vector chaining. This meant the output of one vector pipeline could feed directly into the input of another one.
Like a continuous production line?
Precisely. Created this super efficient overlapping sequence of operations. All this made the Cray 1 vastly more efficient and flexible than its predecessors. It basically set the dominant paradigm for vector supercomputers for almost 20 years. And those design lessons about registers, data locality, managing latency, still profoundly relevant in processor architecture today.
That's such a powerful lesson in optimization, isn't it? It's not just raw speed, it's about the whole system.
Really?
So if we look at these early supercomputing giants, the massively parallel ILEX the 5, the memory-to-memory vector machines like the Star 100, and then Crane's register-to-register approach, they all attack the parallelism challenge differently. What do you think was the single most pivotal architectural leap from that era, the one that really set the stage?
That's a great question. It forces you to distill it down. I mean, ILIAC IV proved SIMD was possible. The Star 100 showed vector pipelines could work, despite the memory issues. But I'd argue Crane's innovation with the register-to-register architecture in the Cray 1 was the most pivotal. It wasn't just about making the processor faster, it was about intelligently managing the data flow to keep that fast processor fed. By bringing data closer in those vector registers and using chaining, Cray showed that an efficient memory hierarchy and smart instruction scheduling were just as critical as raw computational power. That insight, hiding or minimizing memory latency, it became and remains a cornerstone of high-performance design. You see reflected in today's cache designs, multi-core layouts, everything.
Okay, so while Cray was building these absolute beasts, these Formula One machines for the top tier of science, another company, Floating Point Systems, FPS, they were pursuing a different path. More accessible high-performance computing, right? Our report highlights their AP120B from 1975 as a pretty significant milestone.
Indeed it was. FPS really democratized high-performance computing in a way. They created these economical floating-point coprocessors and what they called attached array processors designed to work with mini computers. The AP120B, specifically, became a real workhorse. You found it everywhere in seismic data processing, medical imaging, real-time simulation. It offered a remarkably cost-effective alternative for organizations that couldn't afford or didn't need a full mainframe or a Cray. Architecturally, it was quite something for its time. Ran synchronously at 6 MHz, which sounds slow now, but that was a 167 nanosecond cycle time. Pretty quick then. It had multiple independent pipeline functional units, a 2-stage floating point adder, a 3-stage floating point multiplier, and a 16-bit integer ALU. And to keep these units fed, maximizing bandwidth, it used a dual interleave memory system. By managing to issue results from both the adder and the multiplier on every single clock cycle, it hit an impressive 12 MFLOPS, 12 million floating point operations per second.
That's a phenomenal amount of power for something relatively compact and affordable back then. But the source also mentions it had this unique and apparently quite challenging programming model. What was so different about it?
You're right. The programming model was key to its performance, but also its biggest hurdle. The AP120B was controlled by a single, exceptionally wide instruction word, 64 bits wide. Now, what's crucial here is that different fields within that single, very long instruction directly controlled different functional units, that adder, the multiplier, the ALU, and also specific data movements, all simultaneously within one clock cycle.
Whoa.
So programmers, or these specialized assemblers they used, weren't just writing code in the usual sense. They were manually choreographing every single operation, scheduling data flow through the pipelines, meticulously avoiding conflicts, just trying to keep all those units busy all the time. This design philosophy, basically, pushing the immense complexity of scheduling parallel operations out of the hardware and onto the software. That's the very definition of a very long instruction word architecture, VLIW. And the AP120B was a commercially successful VLIW machine years before the term was even formally coined in 1983. It really highlights this recurring theme in computing, these trade-offs between how complex the programming is versus how simple the hardware can be, all in the name of performance. The takeaway: powerful specialized computation didn't have to be locked away in government labs. It could be accessible, but often it came at the cost of immense, painstaking programming effort.
Okay, so while these specialized processors were finding their niches, pushing the boundaries for specific jobs, there was this parallel, maybe even more fundamental, architectural debate erupting, one that would totally reshape the mainstream CPU itself. This was the famous CISC versus RISC schism. And it wasn't just about how many instructions a processor knew. It was a really profound disagreement about where the intelligence, the complexity, the optimization burden, where that should primarily live in a computing system.
That's an excellent way to frame it. Yeah, a debate about intelligence.
Mm-hmm.
And actually, it raises an important question for us even today. Is there really such a thing as a pure CISC or RISC processor anymore? The answer, as we'll see, is often kinda no. But understanding the original philosophies is absolutely crucial, because this architectural debate fundamentally reshaped how modern processors are built. Its resolution is a major reason why the computer you're using right now is so incredibly fast. So the dominant approach through the 60s and 70s was CISC, complex instruction set computing. The goal was basically make the hardware as powerful and self-sufficient as possible. Complete tasks in just a few assembly language lines.
Right, so CIC instructions were designed to be really powerful, really versatile, often doing multiple low-level things at once, like loading data from memory, doing some complex math, then storing the result back, all in one instruction, almost like a single super-powered command for your computer that bundles a whole sequence of actions, trying to be super helpful right there in the hardware.
Exactly. These processors used variable length instructions, which made decoding complex. They had complex ways of addressing memory, and they relied on this internal layer called microcode to manage all that intricate complexity. The classic examples, the ones that shaped early computing, were Intel's x86 family and the Motorola 68000 series. But then in the late 70s, you had these pioneering researchers, folks at IBM with their 801 project, later at Stanford with MIPS, Berkeley with RISC. They started questioning this whole assumption. Their key observation was, look, despite this huge arsenal of complex CISC instructions, compilers and programmers hardly ever used most of them. Programs actually spent the vast majority of their time executing really simple fundamental operations. Load, store, add, branch, basic stuff. And the overhead of decoding those complex variable length instructions using that microcode layer, it was proving to be a significant drag on overall performance. This critical insight led to the RSC counter-revolution, reduced instruction set computing.
So RSC was pushing for this radical simplification of the hardware itself, advocating for a small, streamlined set of simple, fixed-length instructions. That made decoding much faster, much simpler, right? And the big goal was single-cycle execution for most instructions. Get them done fast, plus this strict load-store architecture. Only load and store instructions touch memory. Everything else happens on registers.
Precisely. And that's exactly why RSC architectures put such a heavy emphasis on having a large number of general-purpose registers. The idea was minimize those slow memory accesses by keeping frequently used data right there on the chip immediately available. The simplicity and uniformity of the RISC instruction set also made it perfect for deep pipelining. Remember the assembly line analogy?
Yeah.
RISC allowed for longer, more efficient assembly lines, executing multiple instructions in an overlapped way, dramatically increasing throughput. But the crucial shift, the big gamble, was deliberately shifting the optimization burden from the hardware to the compiler. RISC architectures bet heavily on intelligent, sophisticated compilers to generate super-efficient code using their simple, predictable instructions. So while CISC aimed to minimize the number of instructions per program, RISC focused on minimizing the clock cycles needed per instruction, even if the total instruction count was a bit higher. And as compiler technology got better and memory got faster, RISC proved to be way more scalable and performant. It's why today even modern CISC processors like Intel's x86, under the hood, they incorporate loads of RISC principles. They actually translate those complex CISC instructions into simpler RISC-like microoperations, which then get executed in their high-performance internal cores. So yeah, your modern CPU is really a testament to the eventual convergence of these two powerful philosophies.
This whole CISC versus RISC thing, it's not just dusty history. It directly explains why your modern CPU, even if it's x86 based, is so efficient under the hood. Okay, so RISC kind of won the architectural argument, and this led to a huge wave of commercial RISC architectures hitting the market. Let's dig into some of the major players that came out of this era.
Yeah, those academic principles quickly found their way into commercial products, spawning this new generation of microprocessors. Each carved out its own legacy. One of the first big ones was SPARC, Scalable Processor Architecture, developed by Sun Microsystems, first released in 1987. It was heavily influenced by the Berkeley RISC project, and SPARC processors powered Sun's hugely successful UNIX workstations and servers. They were everywhere in engineering and science back then. SPARC's defining feature, the really clever bit, was its register windows. Imagine you have a large physical bank of registers, but it's partitioned into these overlapping windows. When you called a function or procedure, the CPU didn't have to slowly save all the current registers to memory and then load new ones. It just shifted its active window. So the outgoing parameters from the calling function instantly became the incoming parameters for the function being called. It dramatically cut down on those slow memory operations for saving and restoring registers during function calls, which happened all the time. And Sun later did something quite visionary. They turned the architecture over to Spark International in '89 to try and foster a broader hardware ecosystem around it.
Okay, interesting. And hot on its heels was MIPs, right? Microprocessor without interlocked pipeline stages. This came from John Hennessy's research at Stanford, and our report calls it the epitome of pure RISC design.
MIPS was definitely celebrated for its clean, elegant five-stage pipeline. Very influential. And its name, without interlocked pipeline stages, points to a key design choice. It deliberately exposed pipeline hazards directly to the software. This meant the compiler was primarily responsible for scheduling instructions to prevent conflicts and ensure everything ran correctly. The most famous example of this was the branch delay slot. An instruction placed immediately after a branch instruction would always get executed, whether the branch was taken or not.
Huh. That sounds tricky.
It could be. It was later seen as maybe a design quirk that complicated coding, but it perfectly encapsulated the MIPS philosophy. Keep the hardware simple and fast, push the complexity to the compiler for optimization. This clean, understandable design made MIPS ideal for teaching computer organization in universities. Loads of students learned on MIPS. Commercially, MIPS chips were the brains behind Silicon Graphics, SGI, workstations. They dominated professional 3D graphics and visual effects for years. And they also had huge success in the early console gaming market, powering iconic systems like the Nintendo 64 and the original Sony PlayStation.
Okay, and not to be left out, there was this powerful alliance that brought us PowerPC, which stood for Performance Optimization with Enhanced RSC Performance Computing. Quite a mouthful. This came out of that big 1991 Apple, IBM, Motorola, or AIM alliance, formed specifically to challenge Intel's growing by 86 dominance, right? And here's a fun fact for you listening. If you played video games in the 2000s, you almost certainly held the power of this alliance in your hands.
That's absolutely right. PowerPC was essentially a single-chip version derived from IBM's high-end multi-chip power architecture. And it quickly proved itself as a robust, superscalar RISC design, meaning it could execute multiple instructions per clock cycle. Very capable. Now, the AIM Alliance didn't ultimately dethrone the Wintel duo in the broad PC market, but PowerPC carved out massive success elsewhere. It became the heart of Apple's Macintosh line from 1994 all the way to 2006, a really crucial era for Apple.
Yeah, the G3, G4, G5 Max.
Exactly. But its real ubiquity, as you hinted, was in video games. PowerPC processors were the undisputed choice for a whole generation of iconic consoles, the Nintendo GameCube, the Wii U, Microsoft's Xbox 360, and Sony's PlayStation 3. Its performance per watt was good. It had strong multi-core capabilities, just perfectly suited for the intense demands of gaming back then.
And finally, we get to Air Advanced RISC machines, the unexpected heavyweight champion, maybe? Our report emphasizes that ARM started out at Acorn Computers in the UK, focusing specifically on low cost and really low power consumption for personal computers.
Yes, and that early focus turned out to be its secret weapon, its greatest strength. The real catalyst for ARM's explosion came in 1990. Apple partnered with Acorn and a company called VLSI Technology to spin off the processor design team into a new independent company. Advanced RISC Machines Ltd., their initial goal. Developed a processor for Apple's Newton PDA. Remember the Newton?
Vaguely. Ahead of its time, maybe.
Definitely. But what set ARM apart wasn't just its elegant, power-efficient RISC architecture. It was a truly groundbreaking business model. Unlike Intel, Motorola, MIPS, ARM didn't manufacture or sell chips itself. Instead, it licensed its processor designs, its intellectual property, or IP cores to other semiconductor companies. This fabulous IP licensing model created this vast competitive ecosystem. Suddenly, dozens of companies could design and produce ARM-based chips for all sorts of applications. And while its competitors were chasing performance for desktops and servers, ARM kept its relentless focus on power efficiency. This made it perfectly suited for the burgeoning mobile and embedded markets, things where battery life was absolutely paramount. So as the world shifted towards battery-powered smartphones, tablets, wearables, IoT devices, performance per watt suddenly became the single most critical metric. And ARM was perfectly positioned. Its dominance today powering over 95% of smartphones and countless other devices. It's not just down to a good RISC architecture. It's equally about that pioneering business model and a design philosophy that brilliantly anticipated where computing was headed.
Yeah, it's really clear that the success of all these different RISC players wasn't just about raw speed. It was equally about finding the right niche, optimizing for specific constraints like power, and having a clever business strategy to get widespread adoption. Really fascinating stuff.
Okay, so while RISC versus CISC was reshaping the main CPU, there was this parallel evolution happening with specialized processors. Just as vital.
chips designed specifically to handle the flood of data coming in from the real-world audio, telecommunications, multimedia. These applications needed real-time responsiveness, intense number crunching, and this led to the rise of the digital signal processor, the DSP.
Exactly. DSPs are a totally distinct class of microprocessor, architecturally optimized for the unique, highly repetitive demands of real-time signal processing. Very different from general-purpose CPUs, which focus more on control flow and varied data tasks. And Texas Instruments, TI, became the undisputed leader in DSPs. Their journey into it actually began kind of serendipitously, with the TMS-5100 speech synthesis chip, developed for the iconic Speak and Spell toy back in 1978.
No way, the Speak and Spell. Yes, that seemingly simple toy demonstrated something profound. That complex digital signal processing algorithms could actually be put onto a single, affordable, dedicated chip.
That's genuinely amazing. Your Speak and Spell toy was a DSP pioneer. And that tech quickly went way beyond toys, didn't it? Finding its way into revolutionary devices like early digital cell phones.
Absolutely. Building on that early success, TI introduced the groundbreaking TMS-320 family in 1983. And this family really established many of the architectural hallmarks that define DSPs even today. So what made them so good at real-time signal processing? Well, it started with a clever trick called a modified Harvard architecture. Imagine having two completely separate rows to your memory. One just for program instructions, one just for data. This let the DSP fetch its next instruction and the data it needed for that instruction at the same time, in one clock cycle. Huge boost to throughput. It was modified because it still allowed some transfers between those instruction and data spaces when needed, like loading filter settings.
Okay, parallel access. Smart.
Then you had the real engine room of the DSP, dedicated multiply accumulate hardware, MRC hardware. This isn't just a fancy name. It's the absolute core of most signal processing algorithms. Filtering, transforms, correlations, they all rely heavily on it. A MS unit can multiply two numbers and immediately add that product to a running total, all in a single instruction cycle, a task that would take multiple slower cycles on a general-purpose CPU. Plus, DSPs often had specialized addressing modes, almost custom-built for specific algorithms, like circular addressing for digital filters or bit-reversed addressing for doing fast Fourier transforms, FFTs, efficiently. And finally, they often included zero-overhead looping, hardware support for repeating code blocks without the usual software fiddling of decrementing counters and checking branches, which wastes precious cycles on a normal CPU.
The TMS-320C25 really stands out in a report as a great example of this evolution. Second-gen DSP, faster, lower power, huge commercial success.
It truly was. The C25 used more advanced CMOS technology, ran up to 50 megahertz, much lower power, higher performance. It found widespread use as a real-time microcontroller for the incredibly precise job of positioning the read-write heads in hard disk drives a critical part of the exploding PC market.
Right, yeah.
And, as you mentioned, crucially, it was often paired with ARM processors to handle the complex signal processing required in the very first digital cell phones. It just clearly shows how specialized hardware like the DSP became absolutely essential for making new technologies practical, things that needed real-time response and intense number crunching in this new digital world.
Okay, so we've covered real-time signals. Now let's pivot to real-time visuals. Another massive demand that blew up, especially in the 90s, was handling the explosion of real-time 3D gaming and multimedia on desktop PCs. Mainstream CPUs, even as they got faster, were struggling with the sheer volume of repetitive calculations needed for, like, rotating 3D models or applying filters to images. They were still doing it kind of one pixel or one vertex at a time, made smooth interactive graphics almost impossible. And this challenge led to the democratization, as you called it, of that supercomputing SIMD concept, bringing it to desktops through SIMD extensions.
That's a perfect description. It was a direct architectural answer to this insatiable hunger for parallel floating point performance that CPUs alone just couldn't deliver for the mass market. SIMD works by packing multiple individual data elements, say 4 32-bit floating point numbers, into a single wider register, often 128 bits or more. Then a single instruction, like ADDPS, add pack single precision, performs the exact same operation on all those packed elements simultaneously. In parallel, this is incredibly efficient for tasks where you need to apply the same transformation to loads of data points at once, like adjusting the brightness of every pixel in an image, or doing the thousands of vertex transformations for a 3D scene.
This is basically why your games look good and your videos stream smoothly today. It's the quiet engine behind so many visual experiences. Intel's MMX 1996, that was the first big one on desktops, but it had limitations, didn't it?
It did. MMX was a pioneering step, absolutely. But it only worked on integer data, which wasn't ideal for floating point heavy graphics. And crucially, it reused the existing FPU registers. This meant you couldn't efficiently run FPU math and MMX operations at the same time. It conflicted.
Okay. Traffic jam.
Kind of. These limitations were significantly addressed with Intel's Streaming SIMD extensions, SSE. Debuted with the Pentium III in 1999, SSE was a major leap. It introduced a whole new set of 8 dedicated 128-bit registers, the XMM registers, plus 70 new instructions specifically for single precision floating point data. This eliminated the FPU conflict, which was absolutely crucial for accelerating 3D graphics pipelines. Around the same time, AMD brought out its competitor, 3D Now, also targeting 3D graphics acceleration, and the evolution just kept going rapidly. SSE2 came with the Pentium IV. It expanded things to handle double precision floating point and a full range of integer operations on those 128-bit XMM registers. That basically made MMX redundant for the most part, and that lineage has continued dramatically. AVX, AVX2, and now the current 512-bit AVX 512 extensions. SIMD has become an absolutely indispensable foundational feature of all modern high-performance CPUs. It's just a prime example of how concepts born in specialized, high-end supercomputing trickle down and become essential for mainstream applications, totally transforming what our everyday devices can do.
Okay, now let's circle back to a concept we touched on earlier. VLIW. Very long instruction word architecture. Our report calls it the logical extreme of RASC's reliance on the compiler.
That's a very accurate way to put it. To really get VLIW, it helps to contrast it with superscalar processors, which is what most modern CPUs are. A superscalar CPU uses complex hardware logic at runtime to dynamically look at the incoming instruction stream, find independent instructions, and schedule several of them for parallel execution simultaneously. The hardware figures it out on the fly.
Okay, smart hardware.
Right. VLIW, on the other hand, completely offloads that entire intricate scheduling task to the compiler beforehand. In a VLIW system, the compiler meticulously analyzes the code, identifies all the operations that can safely run in parallel, and then bundles them together into a single, very long instruction word, could be hundreds of bits wide. Each specific slot or field within that long instruction directly controls a particular functional unit in the processor, an adder, a multiplier, a load unit, etc. This means the hardware itself can be significantly simpler, smaller, and use less power because it doesn't need all that complex runtime scheduling and dependency checking logic. It just executes whatever the compiler has prepackaged for that cycle.
Okay, so if I'm getting this right, VLIW sounds incredibly efficient if you know exactly what your hardware looks like and exactly what you're trying to achieve. Like super optimized, but for something like my laptop, which needs to run anything from Word to some random game I downloaded, programs that are often generic binaries. It sounds like VLIW could be an absolute nightmare.
Yeah.
Is that the big trade-off?
You've hit it exactly. That hardware simplicity and potential efficiency comes at a major cost. A rigid lack of binary compatibility. Code compiled for one specific VLIW configuration, say a chip with 2 adders and 1 multiplier, simply won't run correctly, or maybe at all, on a machine with a different VLIW setup, like 1 adder and 2 multipliers. The compiler has essentially hard-coded the hardware's exact parallel structure into the instruction itself.
Oof, inflexible.
Very. And furthermore, unpredictable events at runtime, like a cache miss where data isn't ready when the compiler expected it to be, can stall the entire processor. Because that meticulously crafted static schedule the compiler created gets disrupted. This inherent inflexibility made VLIW largely unsuitable for the general-purpose computing market, which absolutely demands strong backward compatibility and the ability to run code compiled years ago on new hardware. However, VLIW found its perfect enduring niche in high-performance embedded systems, and especially back in the DSP market. In those areas, software is often tightly coupled to specific hardware, and performance per watt is absolutely critical. The Texas Instruments TMS320C6000 series, the C6X DSPs are a prime example. These chips leveraged VLIW principles brilliantly to achieve extremely high levels of instruction-level parallelism. They became dominant in really demanding applications like wireless base stations, advanced medical imaging systems, industrial control, places where their predictable high performance and power efficiency were invaluable. So it really brings up that core question again. What's the optimal balance between hardware complexity and compiler sophistication? VLIW clearly shows that sometimes pushing more of that intelligence and optimization effort onto the software layer can lead to incredibly efficient specialized hardware. But it definitely comes with significant limitations for broad general-purpose use.
Okay, so this relentless drive for ever higher performance, better power efficiency, it's pushed the industry even further. Beyond fixed function processors, into the realm of truly reconfigurable and even fully custom silicon. Let's start with something really mind-bending. Field Programmable Gate Arrays, FPGAs.
FPGAs are truly remarkable devices. Unlike a traditional processor that just executes a predefined list of instructions, an FPGA is built around this vast grid, a matrix of configurable logic blocks, CLBs, all connected by programmable interconnects like tiny programmable wires. The magic here is that you can actually program an FPGA to become the custom hardware circuit itself. You're not just telling it what sequence of steps to follow. You're defining its very architecture, its internal logic, right down to the level of individual logic gates. You can essentially create digital circuits precisely tailored to a specific task. This tech evolved from simpler programmable logic devices, or PLDs. Xilinx, founded in '84, invented the first commercially viable FPGA, the XE2064, back in 1985. That laid down the basic architecture we still see today.
That's just such a powerful concept. FPGAs, they're like the ultimate shapeshifters of the silicon world. You're not just giving them instructions, you're literally transforming them into the perfect, purpose-built tool for whatever job you need done right now. That level of adaptability sounds incredibly powerful for certain kinds of problems.
It is indeed. And initially, yeah, FPGAs were mostly used for simpler stuff. Glue logic, connecting other bigger chips together, or for prototyping new designs relatively quickly. But as chip manufacturing got better and better, FPGAs got exponentially denser, faster, more capable. Modern FPGAs are incredibly sophisticated beasts now. They often include dedicated hard IP blocks. These are pre-designed fixed-function circuits built right into the silicon for common high-performance tasks. Things like high-speed network transceivers, robust memory controllers, dedicated DSP blocks for signal processing, and even entire ARM CPU cores embedded right alongside the programmable fabric.
Wow, so they have fixed bits too now.
Yeah, the best of both worlds, in a way. A prime example of this convergence is the Xilinx Zinc family. It tightly integrates a powerful dual-core ARM processor system with the traditional FPGA programmable fabric, all on a single die. They call it an all-programmable SoCs, system on a chip. This evolution has massively expanded the role of FPGAs. They're now crucial for hardware acceleration in data centers. Microsoft, Amazon use them heavily. They're vital in AI inference, powering critical automotive systems, and still indispensable for rapidly prototyping the next generation of ASIC designs.
Which brings us neatly to ASICs, application-specific integrated circuits. If FPGAs are the shapeshifters, ASICs are maybe the master craftsmen, the ultimate specialists of the silicon world.
That's a great way to think about it, yeah. An ASIC is, by definition, an integrated circuit customized for one particular, very specific use, not general purpose at all. The absolute goal when designing an ASIC is to squeeze out the maximum possible performance, the minimum possible power consumption, and often the smallest physical size for that one specific task. Whether it's super efficient video encoding, ultra-fast Bitcoin mining, specialized network packet processing, every single transistor on an ASIC is dedicated and optimized purely for that function. The history goes back to early gate array tech in the 60s and 70s, but modern ASICs use highly advanced standard cell or even full custom design methods. The defining characteristic of ASIC development, though, the big catch, is this significant financial trade-off. They come with extremely high, non-recurring engineering costs, NRE costs. The whole process design, verification, creating the manufacturing masks, setting up the production line can easily cost tens, sometimes even hundreds of millions of dollars upfront.
Whoa, that's a huge investment.
It's massive, a huge barrier to entry. But once you've made that initial investment and the design is finalized, the per unit cost of manufacturing ASICs in high volume becomes very, very low, pennies sometimes. And that's crucial for mass market products where every fraction of a cent matters on the bill of materials.
What's really interesting, and our report touches on this, is that FPGAs and ASICs aren't just competitors. They often work together, right? There's this synergy. This kind of explains why some specialized devices start out expensive, maybe using FPGAs, and then get much cheaper later once they hit mass production with an ASIC. It's that journey.
Exactly. Think about a company developing, say, a new type of network switch with a novel packet processing algorithm. They might first choose to implement and test their design using an FPGA. Why? Several critical advantages. Fast time to market, get a product out quickly, virtually zero NRE cost for that initial hardware design, and crucially, immense flexibility. If they find bugs after shipping or want to update the algorithm later, they can just reprogram the FPGAs already out in the field.
Ah, okay. Future-proofing, sort of.
In a way, yes. The higher per unit cost of the FPGA is acceptable for that initial, maybe lower volume production run, or for niche markets where flexibility is key. However, if that product becomes a huge success, sells in high volume, and the core algorithm stabilizes and matures, then the company can justify making that significant NRE investment to create an ASIC version. That ASIC will drastically cut the per-unit manufacturing cost, consume far less power, improve profit margins, and probably allow for a smaller, sleeker device. So yeah, FPGAs often serve as the ideal prototyping, development, and market validation platform for future ASICs. It's a strategic choice, driven entirely by economics, market demand, and where the product is in its life cycle.
And all these threads, all this incredible specialization, the evolution from optional coprocessors to embedded DSPs, SIMD, VLIW blocks, FPGAs, ASICs, it all truly comes together in the modern system on a chip, the SoC. Our report aptly calls it the ultimate culmination of the coprocessor's long history.
That's precisely right. The modern SoC isn't just a single chip anymore. It's an entire electronic system, integrating all the crucial components onto one tiny piece of silicon. And the smartphone SoC. That's arguably the masterpiece of this entire era, a prime example of what we call heterogeneous computing. These chips contain this multitude of highly specialized processing cores, all working together orchestrated on a single die. For instance, you'll typically find a multi-core general-purpose CPU, usually ARM-based, handling the OS, apps, general control flow. Right alongside it, a powerful GPU for rendering all the 2D and 3D graphics for the user interface, games, video. But it doesn't stop there, not even close. You'll also find one or more DSP cores, maybe like TI C7X, specifically designed for efficiently processing audio, voice commands, sensor data in real time. No power stuff. Then there's an image signal processor, an ISP. That's usually a dedicated ASIC optimized for handling the raw data, pouring off the camera sensor, doing noise reduction, color correction, sharpening, all that magic that makes your photos look good. There's likely a separate video encode-decode engine, another ASIC, efficiently compressing and decompressing video streams for recording or streaming without killing your battery. And more recently, we've seen the widespread integration of neural processing units, NPUs, or other AI accelerators, purpose-built hardware for machine learning tasks, facial recognition, natural language understanding, computational photography features. And then, of course, there are countless other specialized blocks. Security modules, complex radios for Wi-Fi and cellular, sophisticated power management units. It's incredibly dense.
So what does this all mean for us, the users holding these incredibly sophisticated devices? It really sounds like our phones aren't just a computer anymore. They're more like Gekka, an entire symphony orchestra of tiny, highly specialized computers, each one a master of its own instrument, all working together in perfect harmony, hopefully.
That's a fantastic analogy. And connecting it to the bigger picture, the SoC perfectly illustrates that the era of the monolithic, do-everything general-purpose computer is largely behind us, at least in these kinds of devices. That concept of the coprocessor, it's completely transformed. It's no longer a separate chip you plug in. It's now an IP core, a licensed, pre-designed functional block seamlessly integrated into the larger SoC design by companies like Apple, Qualcomm, Samsung. The ability to dynamically dispatch each subtask to the right processor for the right job within that single piece of silicon. That's the absolute essence of why our devices are so powerful, yet also so power efficient and versatile today. It's all about achieving the optimal blend of performance and energy use by intelligently distributing the workloads. Maybe we can quickly recap the strengths that drive these choices, because each technology really excels somewhere specific. The CPU, super programmable, very versatile, great for general computing running the OS. But its peak performance on specialized tasks, often low to medium. Power efficiency can be lower for those tasks too. Development cost is lowish, unit cost medium. Ideal use case. General computation and control.
Okay, the jack of all trades.
Right, the GPU. Highly programmable for its domain parallel graphics, data processing, very high peak performance for those parallel tasks. Power efficiency is medium. Development cost low once the architecture exists, but unit cost can be high due to complexity and memory needs. Ideal use case. Graphics and parallel data processing.
The visual powerhouse.
Exactly. DSPs.
Yeah.
Highly programmable for signal processing. Incredible peak performance for those real-time tasks, and excellent power efficiency doing them. Low development cost, medium unit cost. Ideal use case. Real-time signal processing, audio, sensor fusion.
The real-time specialist.
Then FPGAs.
Unique.
Hardware reconfigurability. Medium to high performance, medium power efficiency. The big win. Near zero NRE cost. Huge flexibility for prototyping. But the per unit cost is relatively high. Ideal use case. Prototyping, low, medium volume production, evolving algorithms, acceleration.
The shapeshifter.
And finally, ASICs. Zero programmability, fixed function. But highest possible peak performance, highest power efficiency for their specific task. Development cost, very, very high NRE.
Right.
But per unit cost and high volume, very low. Ideal use case. High volume, stable algorithms, maximum performance efficiency.
The ultimate custom tool. Wow, okay. That incredible mosaic, that orchestra of specialized components, that's precisely why your smartphone can just effortlessly switch between playing a high-end game, doing a crystal clear video call, complex photo editing, navigating with GPS, all without melting in your hand. It's not one chip struggling to do everything. It's this whole ecosystem, each specialized part doing what it does best, all seamlessly orchestrated. Amazing, really. Hashtag tag outro. Wow, okay, what an incredible journey we've taken today. I mean, starting from an optional math chip that maybe sped up your spreadsheet, all the way to this entire intricate ecosystem of specialized processors woven into a single tiny piece of silicon in your pocket. The coprocessor has undergone this astonishing transformation. It really has gone from being like an external accessory to being the absolute integral essential core of virtually all modern computing.
This deep dive really hammers home that the relentless pursuit of performance and efficiency has always been the primary driver of architectural innovation in computing. And the core idea that for the most computationally demanding challenges, the most effective solution is, and arguably always has been, specialized hardware that remains a truly enduring principle. It's just a testament to the ingenuity of engineers constantly finding ways to push those boundaries.
And this story is absolutely not over. Our report also touched on this new class of workloads that are once again pushing the limits of general-purpose hardware. Artificial intelligence, machine learning. We're already seeing this whole new wave of dedicated AI accelerators emerging, things like the neural processing units, NPUs, in our phones and edge devices, and Google's massive tensor processing units, TPUs, and data centers.
Which raises a really important, maybe provocative question for you, the listener, to think about. As you reflect on this incredible history of specialization, what new, maybe currently unforeseen computational challenges do you think are just over the horizon? And what amazing, highly specialized hardware do you imagine will emerge to tackle them, continuing this timeless legacy of innovation? What tasks, maybe previously unimaginable, will you end up relying on these future specialized chips for in your daily life or your work?
Thank you so much for joining us on this deep dive into the truly fascinating, intricate world of coprocessors and specialized computation. We really hope you gain some incredible insights and maybe now have a renewed appreciation for the silent, powerful workhorses constantly humming away inside your pocket and on your desk.